All right, this is section 11.5, powers and roots of complex numbers. So let's start with this idea of if we were to use the idea of multiplication we learned last time to raise a number in polar form, a complex number in polar form, to a power. We can do that, of course, because powers are simply multiplication. It's done repeatedly. So, of course, squaring this will be multiplying it by itself. And we know how to multiply now is that we multiply the r values, so that'll be r times r, and we add the angles, theta plus theta, and of course r times r is more simply written as r squared, and theta plus theta is more simply 2 theta. So if we were to do something very similar by cubing, I'm not going to write this one out, thank goodness. Slow to write the expanded form. But if we were cubing, the result would end up being r cubed cosine of 3 theta plus I sine of 3 theta. So what we can glean from this is that raising a complex number in polar form to a power is actually quite easy. So the formula for that is r times cosine of theta plus I sine of theta to the nth power will be r to the nth times cosine of n theta plus I sine of n theta. So we raise the r to the power of n, we raise the r to the power of n, and we multiply the theta by n. And the compact form of that, r cis theta raised to the nth, is r to the nth cis n theta. And so that's a nice pair of formulas that you should probably make sure you know, commit to memory. Right. So all right, let's do an example. 1 plus I square roots of 3 raised to the 8th. Now you don't want to multiply this binomial times itself and times itself and times itself, etc., and get the answer that way. So the first thing you're going to want to do is to rewrite that number in polar form. So let's think about what that would be. The x is 1, the y is square root of 3, and so r is the square root of x squared plus y squared. So r is the square root of 4, which is 2. And then if we plot that point to make sure we get the right quadrant, 1 plus square root of 3 is about right there. So, of course, this is 1 and this is square root of 3. So we know that our angle is a 60-degree angle. So, therefore, we want to rewrite this in polar form. It's 2 cis 60 degrees raised to the 8th. So the first part of this is to convert the rectangular version of the complex number into its polar form, and then use the formula we just developed. That's 2 to the 8th cis 8, which is n, times 60 degrees. 2 to the 8th is 256 cis 8 times 60 degrees is 480 degrees. And then remember, we generally would like to deal with that as an angle between 0 and 360 degrees. Makes life easier. So if you subtract 320 to get a coterminal, 360 degrees from that to get a coterminal angle, you should get 120 degrees. That's where that 20 came from. I was getting ahead of myself. Okay, so that is 256 cosine of 120 degrees plus I sine of 120 degrees. So 120 degrees, of course, is right here. It's this angle right there. So this is -1 square root of 3 and 2. So that gives us a cosine value that is -1/2 and a sine value that is positive square root of 3 over 2 times that I. And then when you distribute, you get -128 plus 128 I square roots of 3. Okay. And by the way, I forgot to say, the gentleman who came up with this multiplication, repeated multiplication, the exponentiation, is a gentleman by the name of de Moivre, and this is de Moivre's theorem. So let me say, write his name here. This is de Moivre's theorem that follows. That's what's starred here, de Moivre. And I don't speak French, so I'm probably mispronouncing this. I've had several French speakers listen to me pronounce it, and they've given me a tentative thumbs up. So hopefully it's not too awful. But de Moivre's theorem. And so if that's referenced, you'll know that it's referencing this formula right here. Okay. So, now, the reverse of that, if you will, is the nth root. So we're going to be finding roots of complex numbers. We just found how to do powers of complex numbers. Now we're going to find out how to do roots. If we had this equation, a plus bi, that was raised to the nth, and the answer ended up being x plus yi, we would call a plus bi an nth root of x plus yi. Let me make this an example that you would understand a lot better. If I said 7 cubed is equal to 343, then I would be saying that 7 is a cube root of 343. So hopefully that makes sense to you. Now, one thing I've been saying here on purpose is a cube root. One thing you ought to know from an algebra course that you took at some point, maybe you never practiced it much, but it's true that if you have a quadratic equation, let's make this easy to start with. There are two results to this, okay? Two results, two square roots, two numbers that would make that true, -5 or +5. And the way you could solve that, I know that's a really easy one, but I'm going to give you an example that goes further than just this easy one. We would get it equal to 0 and factor. And then by setting the factors equal to 0, we get those two answers. Okay? So, I'm going to claim that an equation of the form x to the 4th equals 16, I claim it has 4 answers. And at first you may think, oh, that can't be. You just take the 4th root on your calculator and you get the one answer. Well, if you take the square root of 25, you only get 5. So it stands to reason that the calculator is only returning one of the many answers we should get. For a quartic equation, a 4th degree equation, there are 4 answers. So I'm going to set equal to 0 and factor. That's a difference of 2 squares, which factors to be x squared plus 4 times x squared minus 4. And using the normal rules of factoring, the sum of 2 squares isn't supposed to factor, and we're not going to right now, but the difference of 2 squares does factor. So this factors to be x plus 2 times x minus 2. If you set each of those factors equal to 0, you'll get that x squared equals -4, or x equals -2, or x equals 2. And if you take the square root on this first one, on both sides, you'd need to put in a plus or minus the square root of -4, which means that the other two answers, besides 2 and -2, are positive 2i and -2i. And so those are the 4 answers. to that quartic equation. So, how are we going to deal if we had a cubic one? Well, let's see. We had x cubed equals 8. Subtract 8 from both sides and factor. And of course, you all learned how to factor a difference of two cubes, right? You take the cube root of the first thing, keep the sign, take the cube root of the second thing, and then ignoring the original problem, I'm going to look at the binomial I just wrote, square the first thing, change the sign, so plus, then multiply those two things, x times 2 is 2x, then write plus, and then square the second thing. The square of negative 2 is 4. Okay, so setting each of those factors equal to 0, I get x equals 2. And by the way, that one is called the principal root. It's the one you'd get on your calculator if you did cube root of 8. If you did the 4th root of 16, x equals 2 is the principal root. If you did the square root of 25, you'd get x equals 5. So I'm going to be talking about the principal root later. Again, I'll use that term, and so I want you to know what it is I'm talking about. It's the easy answer, the one that's you can get first. Kind of the no-brainer one, I guess, no manner of speaking. Okay, to solve this other equation, x squared plus 2x plus 4 equal to 0, it doesn't factor, so I'm going to have to use the quadratic formula, which is x equals the opposite of b plus or minus the square root of b squared, 2 squared is 4, minus 4 times a, which is 1, 4 times 1 is 4, times c, which is 4, so that'll be 16. Again, that was opposite of b plus or minus the square root of b squared minus 4ac, all over 2 times a is 1, so 2 times 1 is 2, and that simplifies to be negative 2 plus or minus the square root of negative 12. Then the simplification of that radical, the negative sign comes out as an I, and 12 is 4 times 3. The square root of 4 comes out as a 2, and the square root of 3 is still there because it's not a perfect square. And then if you distribute that division of 2 to each term on the top, you get negative 2 divided by 2, which is 1, plus or minus 2i squared to 3 over 2 leaves the square root of 3 times I, or I square root to 3. Okay, so those are the three cube roots of 8. 2, negative 1 plus I squared to 3, and negative 1 minus I squared to 3. And as you can imagine, I'm pretty good at this, and I imagine, you know, I could find 5th roots and 12th roots and all that kind of stuff eventually by factoring and using different things that I know. But I'm thinking some of you may have gotten lost in all the stuff I just did, and I'm thinking it's not the easiest thing in the world. Finding the roots of complex numbers is not going to be that hard. So this is kind of a nice thing. But so that we can get an idea of where I'm going to head with this, if I had graphed in the complex plane, so this is the real axis, and this is the imaginary axis. Both of my results for x squared equals 25. I'm going to graph all of these, so there are going to be several graphs that look kind of like this. Then that would be at 5 is one answer, and negative 5 is the other. Okay, well, based on one example, you're not going to see much of a pattern, so kind of keep that one in mind. Now let me do the x to the 4th equals 16 graph. The graph of the fourth roots of that number 16, I should say. So this is the real axis. This is the imaginary axis. So 1, 2, 3, 1, 2, 3, 1, 2, 3, negative 1, negative 2, negative 3. Okay, so if I graph those, the principal root is positive 2, and negative 2 is another answer, and 2i is another answer, and negative 2i is another answer. Okay, maybe you're starting to get a glimmering here of where I'm headed, but I'm not going to give it away yet. I still want us to think about this and see if we can make sense of it. So let's graph the answers we just got from x cubed equals 8. Okay, so put several marks on each axis. Probably 3 in each direction is plenty here. Okay, so let's plot these answers. The principal root is 2. Then the next one is negative 1 plus I squared, it's a 3. Negative 1 is the real part, so I'm going to go left 1. And square root of 3 is the imaginary coefficient. And the square root of 3, let me type that in my calculator, I think it's about 1.7. But yeah, 1.73. So that means I'm going to go up here to about 1.73, and there's that one. And negative 1 minus I squared is a 3. That's going to be about right there. Okay, so let's see if you can tell me what the connection is. Well, the one I thought where you'd get it most is this one over here, where we started with x to the fourth equals 16. If I were to draw a circle centered at the origin, pretend like that little bump didn't happen just then. If I were to draw a circle whose radius is the real number 2, then all of the answers for x to the fourth equals 16 are on that circle, and they're spaced evenly around that circle. In fact, this answer being at, say, 0 degrees, the next one's at 90. We're moving 90 degrees each time to get the next answer, right? Agree? So how would I know that it's 90 degrees? Well, I have how many answers? 4. How many degrees are in a complete circle? 360. So if I take the degrees in a full circle and divide it by the number of answers I'm anticipating, that's going to be the spacing between answers. Okay, well, let's see if that's just a coincidence or that's a real thing. I don't have an axis, y-axis, or imaginary axis scale, but imagine a circle of radius 5 up here. I should have picked a smaller number. There are 2 answers, and they're equally spaced on that circle. And I claim that the spacing would be, if I can get one in the right place, the principal root in the right place, and I divide 360 degrees by the number of answers I'm anticipating, then they should be spaced 180 degrees apart. So this one's at 0 degrees, and this one's at 180, and we're done. That's all of them. Okay, so let's check this third one. If my principal answer is 2, and I draw a circle of radius 2, so I'm going to have to put some dots here to make sure I kind of hit where I'm going. That circle of radius 2 is going to look like this. And even if my graphing isn't perfect, those points are actually all on that circle, and I claim that the spacing between them should be the full circle divided by 3, so every 120 degrees. So this should be at 0 degrees, because it was a real number, and 120 degrees later, I get my next answer, and 120 degrees after that, I get my next answer. And of course, if I add 120 to that, I get 360, which means I've gone all the way around. And those are my 3 answer locations. So, what would the polar form of these answers be? That's actually a whole nother thing to consider. Let's go to this one. The first one would be that x is 2 cis 0 degrees, because the radius is 2, right? And the angle is 0. The next one is 2 cis 90 degrees. The next one is 2 cis 180 degrees. And the last one is 2 cis 270 degrees. Okay, this is looking pretty good. So when I talk about how to find these examples I think will really be of great benefit, so that these answers that are in rectangular form, 5 and -5, that's going to be 5 cis 0 degrees and 5 cis 180 degrees. By the way, writing the polar form for a point that's on the real or the imaginary axis is easy, because it's a quadrantal angle, 0 degrees, 90 degrees, 180 degrees, 270 degrees. Those are super easy. So make sure you know how to do those without beating your head up against the wall. Okay, so for the last one, the 3 answers are, we have a radius of 2, so 2 cis, the first one I got is at 0 degrees. The next one is 2 cis 120 degrees. And the last one is 2 cis 240 degrees. And if you were to get these answers that I wrote in red first, how hard would it be to convert that to the rectangular form? Like 2 cis 120 degrees would be 2 times the cosine of 120 degrees plus I sine of 120 degrees. You draw the 120 degree angle, you get your right triangle, 1, 2, square root of 3, boom, boom, bing, bop, boom, and you're done. It's really not going to be that hard. That's kind of the background for what we're doing here. And I kind of went off book for a while, so hopefully that all made sense. So if I had now a more generic form, we know that, for example, r cosine alpha plus I sine of alpha is some complex number, and if we were to cube it, the result would be something. And the question I'm looking at is to find the 3 complex cube roots of that number. So we're going to find the cube roots by saying, well, whatever the answer is, it cubed will be 8 cosine of 135 degrees. This is the number that was given, plus I sine of 135 degrees. Okay, so if we think about the left side and use de Moivre's theorem, that would be r cubed cosine of 3 alpha plus I sine of 3 alpha would equal 8 cosine of 135 degrees plus I sine of 135 degrees. Okay, so equating the parts of the two sides to each other, that means that r cubed has to be 8. And taking the cube root, that means that our r will be 2. Okay, so our circle will have a radius of 2 that we might draw if we were drawing the pictures as I did above. Then 3 alpha is equal to 135 degrees plus see, because that's just one answer and we need to make sure that we get all of them. And so if we wanted to get all angles, remember we can add, it's like adding 2 pi k, but this is in degrees, so this would be 360 degrees k. And then if you divide by 3, you get 45 degrees plus 120 degrees k. So this is where I kind of do it a little bit differently from what the book does. Is I'm going to write this differently. This is what I would have written. 3 alpha equals 135 degrees. Solve for alpha. It's 45 degrees. And that's my primary answer. And then, since it's something cubed equals our number, that means that the full circle is going to be divided by 3 and get 120 degrees spacing between my answers. Their way, you're going to get the same thing. Notice the 120 degrees k right here. If you let k equal 0, you'll get the primary answer 45 degrees. Then let k equal 1 and 2, and you'll get the other two answers. I just don't use a formula like that. I find the principal angle and then divide 360 by the power whose root we're trying to find here. Divide by 3 because it's something cubed is equal to our number. And then just start with our primary answer and add 120 degrees to get my total of 3 answers. So, at any rate, what that means is that one of our roots is, change this a second, one of our roots would be 2 cis 45 degrees. The next one would be 2 cis, and now I'm going to take 45 plus 120 to go to the next one, and that's 165 degrees. And then 2 cis, and then starting with 165, add 120, that's 285 degrees. And those are your 3 answers. If you want to use their formula and let k equal 0, 1, etc. until you get up to n minus 1, since we're raising it to the power of 3, the largest k you use is 3 minus 1, 2. So you start with k equals 0 and go up to your power minus 1. And if you want to do that, it's fine. It'll work. It's not bad or anything. I'm just saying I think my way is a little bit faster. And if you understood the graphical nature of splitting the circle into equal portions, and that's the angle that you change by to get all of those angles. This down here will seem easy to you, and that's what my hope is that that's going to work. Okay, so if I want to find the 2 square roots of 4i, so the first thing I would do, it would be to rewrite our number that we're given in polar form. So if you think about 4i, I'm not going to, this is the real axis and this is the imaginary axis. I'm not writing the whole thing for sake of time. And so this is up here at 4i. And so what angle is that? 90 degrees. How far is that from the pole? 4 units. And so this is pretty easy. Remember I said the ones on the axes are easy. It's 4 cis 90 degrees. Okay. Actually, this time I think instead of using degrees, because we haven't done it yet, I want to use radians instead. So pardon me for writing the 90 degrees. I really want to use radians here for practicing with them. So let me erase that 90 degrees. And of course, what is the angle in radians? Well, it's pi over 2, right? Oops. So the angle here is pi over 2. So this would be 4 cis pi over 2. Okay. Now, we want to find something that when squared gives us that. We're looking for the square root. So r cis alpha squared would give us that number, and r cis alpha will be the form of our answers. So again, that means that 4 cis pi over 2, using Dua's theorem, that's going to be r squared and cis of 2 alpha, equating the corresponding parts. That means r squared is 4, so r is 2. And equating 2 alpha to pi over 2, we'll get our principal angle, alpha, which is pi over 4. Okay, so alpha equals pi over 4. Then, to find the spacing between angles where the answers lie, we're going to take the full circle, which in radians is 2 pi, and divide it by the number of answers we're finding. Since it was square roots, because it's a squared thing, we're going to divide by 2, because there'll be 2 answers. They'll be spaced pi apart. And so what that means is that our answers are going to be 2 cis pi over 4, and the other angle is going to be pi over 4 plus pi. That's going to be 2 cis 5 pi over 4. Okay, and that's the complex number written in polar form. The directions say to write those in rectangular form, so we'll go one step further here. It may take us several steps to get there, but it's one basic step. So that cis pi over 4 means cosine of pi over 4 plus I sine of pi over 4. And the other one will be 2 cosine of 5 pi over 4 plus I sine of pi over 4. Okay, so just to make sure that everybody knows what we're doing here, pi over 4 is here. This will be 1, 1, square root of 2. And 5 pi over 4 is right here. That's going to be negative 1, square root of 2. Okay, so cosine of pi over 4 is square root of 2 over 2 plus I times the sine of pi over 4, which is also square root of 2 over 2. The other one will be 2 times cosine of 5 pi over 4 is negative square root of 2 over 2 plus I times the sine of 5 pi over 4, which is also negative square root of 2 over 2. And then distributing, you get square root of 2 plus I square roots of 2 is one of your square roots of that number, and negative square root of 2 minus I square roots of 2 is your other square root of that original number. Okay. Next one. Okay, find all the fourth roots of something. So we're going to start with the idea that some generic number is an answer for us, r cis alpha to the fourth will give us our original number that they gave us. Okay, so in order to do this well, we're going to need to convert that given number into its polar form. So let's go off to the side and do that. We'll let x be negative 8. Y will be 8 square roots of 3. We should probably think about where that graph is. Negative 8 plus I, that's going to be up here someplace in the second quadrant. Not necessarily drawn to scale. Doesn't really have to be. It's fine. But since this is the 8 square roots of, well, we'll get back to that. So that means that r is the square root of x, which is negative 8 squared, plus y, which is 8 square roots of 3 squared. See, negative 8 squared is 64. And 8 squared is 64 times square root of 9 is 3, so 64 times 3, which is 256. When you add all that together, and the square root of 256 is 16. Okay, and then the tangent of theta is y over x, which is negative square root of 3 over 1. Okay, so picturing that, I'm going to use the picture up here. It wasn't drawn to scale, and I kind of left it that way on purpose. Oh, what? Yeah. So the x is the part that's going to be our negative 1 because of the quadrant we're in, and y is going to be the square root of 3. And of course, our reference angle there is 60 degrees. And so that means that our angle here is 120 degrees. That's our base angle for our basic primary answer, the principal answer, if you will. We'll start there. Well, wait a minute. I'm sorry. I'm getting ahead of myself again. Sorry. What we were doing was finding out what negative 8 plus 8i squared to 3 was in polar form. And so that's what we've done. We haven't found a principal root or anything yet. Sorry, got ahead of myself. So that's 16 cis 120 degrees. That's what that number is. All right. So using Demoivre's theorem on the left side, that will become r to the fourth cis 4 alpha, which is equal to 16 cis 120 degrees. So equating the like parts of that, r to the fourth equals 16. The principal root of 16 is, fourth root of 16 is 2. So that's the one we'll use. And our 4 alpha would be equal to 120 degrees for our first answer. So alpha starts at 30 degrees. Then the full circle is 360 degrees. We're finding 4 answers, so we're dividing 360 degrees by 4. So they'll occur at intervals of every 90 degrees. Another one will happen. So our answers are, the first one is 2 cis 30 degrees. The next one is 2 cis 30 plus 90 is 120 degrees. The next one is 2 cis 120 plus 90 is 210 degrees. And the last one is at 2 cis 210 plus 90 is 300 degrees. Okay, so we should only have 4 answers, and there are those. And then if we were to take the time to go through all these like we've done before and convert them to the rectangular form, so the first one would be 2 cosine of 30 degrees plus I sine of 30 degrees, and simplify, distribute the 2. This is what you'll get. Square root of 3 plus I is the first one. The next one is negative 1 plus I squared to 3. The next one is at negative square root of 3 minus I. And the last one is 1 minus I square root of 3. Okay. And if you were to look at these on a graph, there would be a radius 2 circle upon which they would all fall. This is in the complex plane, by the way, this circle is. Pretend like that's a circle. This is the real axis, of course, and this is the imaginary axis. And so our very first answer was square root of 3 plus I, which is about right there. And of course that's the angle 30 degrees. And then the next one was negative 1 plus I squared root of 3, which is about right here. And of course that's the one that's 120 degrees. The next one is negative square root of 3 minus I, which is about right here, which is the 210 degrees. And then finally, the last one is at 1 negative I squared to 3, which is about right there. And if we represent those complex numbers as vectors, they can draw this in. I never have drawn these as vectors in my studies, but that's okay. That's what this book does. I just plot them as points. Anyway, those are the 4 answers, and of course they're equally spaced around the circle, as we said. All right, so let's go to the next example. This one says, find all complex number solutions of x to the 5th minus 1 equals 0. And it does say graph them as vectors in the complex plane. So I'm going to get x to the 5th by itself, and x to the 5th equals 1. So we want to find an R cis alpha in complex form when raised to the 5th is equal to 1 in rectangular form. And so if we were to graph 1, real imaginary, pretend like I wrote the entire word, 1 is right there, and so it's 1 cis 0 degrees. Okay. So using de Moivre's theorem, that'll become r to the 5th cis 5 alpha equals 1 cis 0 degrees. And equating the various parts that should be the same, and r to the 5th should be 1, 5 alpha should be 0 degrees, and the principal root of the 5th root of 1 is 1, and 0 divided by 5 is still 0 degrees. Then the spacing of these will be the full circle, 360 degrees, divided by the 5 answers we're finding. And so we get 360 divided by 5, which is 72 degrees. Okay, so our answers are 1 cis 0 degrees, then 1 cis 0 plus 72 is 72 degrees. Then we'll add 72 degrees to that, so that'll be 1 cis 144 degrees. Then add 72 degrees to that, and that should be 1 cis 216 degrees. And finally, add 72 to that, and you get 1 cis 288 degrees. And make sure you stop when you have your number of answers. Since it was 5th roots, or x to the 5th was the original thing, we should have 5 answers. So don't go to a 6th, 7th, or 8th, because those are actually just repeating ones you've already found. Okay. So, if we were to graph these, move this down a little bit. If we were to graph these results in the complex plane, this is the real axis, this is the imaginary axis. And because the modulus, the radius, is 1, I'm going to make my marks on the axes fairly large. So that's 1, and that's I. There. This is -1 and -I. And so if we graph this set of answers at 0 degrees on, well, let me draw the circle of radius 1. Whoops. Let me try that again. Well, that doesn't look very circular. Sorry. Pretend like it's wonderful. All right, so the first answer is on that circle, 1 away from the origin, at 0 degrees, and then at 72 degrees, then at 144 degrees. Let's see, what would that be? About right here. And then 216 degrees, and then 288 degrees. And we're supposed to draw those as vectors. And those vectors should be equally spaced. Those 5 vectors should be equally spaced around the circle. Of course, that sort of depends on how carefully you graph those. I was just sort of guessing where they fall, but it is accurate, just not pretty. All right, so that ends this section. Have a great day. I will see you in class.